Alright, so this video is going to go over the example problems from the other day, giving you the solution method to each of them. So it's going to be broken into parts. The video is going to start off by first presenting the example on the screen, then followed by working through it. Okay, so just like I said, skip to whatever you need help with. Alright, so the free body diagram is already drawn out. Also, the values that are given are filled in. It just said that the object is being pushed at a constant velocity, so keep that in mind. And the applied force is 96 newtons. And the problem asks you to find the weight of the object. That's going to be the force of gravity acting on it, the normal force acting on it, the force of friction, and the coefficient of friction, which is mu. So to work through this, the constant velocity thing is going to tell us something very important. It's going to tell us that the net force is equivalent to 0. That means that Fx net is equal to 0, and so is Fy. Right? Both of those values are going to equal 0. That tells us that Fn and Fg are equivalent, and it tells us Fa and F of F are the same. So right off the bat, we already know the answer to the force of friction. So F of F is equal to Fa, which means it is 96 newtons. So we already have one of these taken care of. The next bit is figuring out the force of gravity. Since we know the mass and we know this thing is going to be on Earth, we can go ahead and figure out what Fg is. So Fg is mg. Plug in the values and see what that comes out to. Alright, so we get 117.72 newtons as our force of gravity. So that is another one of the things we needed. And because of the fact that our net force in the y direction is equivalent to 0, that means we also know Fn. Because Fg is equivalent to Fn because of this. So there's our next one. Now that we know all of the forces acting on the object, we can go ahead and find the coefficient of friction. So we're looking for mu here. Now to look for mu, you're going to go ahead and use the equation with mu equals force of friction over force normal. And then plug in the values that we have for all those different variables. And mu value comes out to 0.82, and keep in mind, mu is a unitless value because it is a force value divided by a force value, so therefore it is unitless, okay? And that's it for number 1. Alright, so for number 2, we've got all the free body diagram and the values all done. Put it in there. We need to figure out the values listed here in the bottom right. We want to know what is the mass of the sculpture that the curator is pulling, what is the normal force, what is the force of friction, and what is the applied force. How much force is he applying and pulling the sculpture to achieve that acceleration of 0.5. So first thing off is we are told that this thing is accelerating, which means that the net force in total is not 0, however that part of it still is. The net force in the y direction is still 0 newtons because these two values are balancing out. Our other two, friction and applied, are just in the x direction, and same as before. We know the statue is not hovering or anything like that, so these values have to be equivalent. So that tells us down here that our Fn then is just going to be the same as Fg, so it's the 1470. Now the next bit. We have this value. We need force of friction, but in order to find out force of friction, we would need to know force normal, which we do now know, and we have mu k, so let's go ahead and find that. And we get 838 newtons as the force of friction acting on the sculpture. So now that we have Ff, we need to work towards finding out either the mass or the applied force. Since we know the force of gravity acting on the sculpture, we can go ahead and find the mass with the Fg equation. So now we have mass. Mass is 149.8 kilograms for that sculpture. Now with the mass, we can figure out the net force because we know what the sculpture's acceleration is. So now we can find out F net in the x direction. That is equivalent to MA. Just going to go ahead and call that 75 newtons. Now that we know the net force, which isn't something we needed to know, but it's something we can use to figure out the applied force, because this net force is also equivalent to all of our x components. So we have an applied force to the right, and we have a force of friction to the left. So this 75 equals those two together. There we have it. The curator is applying a force of 913 newtons in order to pull that sculpture with that value of acceleration being 0.5. And that's it for number 2. Next up was 3. Alright, so here is number 3. We have the free body diagram drawn out. We have the values that are given, which are mu static, mu kinetic, the time at which the person is pushing the flower forward, and the mass of 11 kilograms. And I know probably the first thing, if it did cross anybody's mind, I hope it did, how are we pushing a flower? That's irrelevant. So the values in red are what we're going to be solving for. The values with the blue dots next to them are what it actually asks for, but in order to get those values, we're going to need to solve for all of the rest. So to start off, we're given the mass of the flower. Let's go ahead and figure out the weight of it, and then go ahead and solve for the normal force and the net force in the y direction. Since this thing is acted upon only horizontally by friction and applied force, that tells us vertically speaking that value has a net force of 0, so we know Fn and Fg should be the same. So I'll put those equations on the right hand side. Go ahead and solve through them for yourself and see if you get the same answers. So we have 107.9 for both of those. So we have answered these. So now that we have that, we can go ahead and figure out our force of friction. Because we need to figure out what that force of friction is in order to figure out how much force we need to apply in order to get the plant moving. Because in order to get an object moving, you have to overcome the force of static friction. Now, we figured this out. To get that minimum value, we're just going to solve for f of f. Now, to get the thing moving, you would actually need to apply ever so slightly more than whatever ff happens to be, but for the sake of problems, you're just going to solve and give the answer just equivalent to whatever ff is. Now, it says at that point in time we have this plant moving. We're going to continue to apply that same amount of force for a time of 3.75 seconds. Now, how far does the thing move in that amount of time? Well, to figure out how far that thing moves, we need to know how quickly it is accelerating. Go back to the kinematics equations from the beginning of the year. So let's go ahead and figure out the acceleration by figuring out what the net force is on the flower. And the net force on the flower, looking at our diagram, is the applied force minus the force of friction. Now the force of friction we're dealing with when this flower is moving is kinetic friction. So that's FFK. Now we haven't found out this force of friction kinetic yet, but we can go ahead and just nest that right into the problem. We know that the force of friction equation we've already used is mu times force normal. We just have to insert that with the kinetic mu instead of the static mu. And our total net force in the x direction comes out to then 34.5 newtons. So we ticked off another thing down there on the bottom left. So now we have the net force in the x direction. We can then use Newton's second law with this to find out the acceleration. So now we have A. The flower is accelerating at the 3.14 meters per second squared to the right. Now that we have this, we can find the last bit of information we need, which is how far the flower travels in that 3.75 seconds. And to do that, go back to the kinematic equations. Delta x is what we're looking for. We have a VI of 0. The flower started off at rest. We know the time, 3.75 for both t values, and the acceleration of 3.14. We get 22.1 meters as our final answer for how far the flower goes. And with that, we have solved everything we needed to for number 3. All right, so here is number 4. We have a 20 kilogram boy and a 5 kilogram skateboard coasting from 4.5 meters per second to rest over a course of 20 meters. We want to figure out what is the deceleration of the skateboarder, what is the force of friction acting between the skateboarder's wheels and the surface, and what is the mu. In this case, since the thing is rolling, that's going to be mu rolling. Okay, so let's go ahead, and the diagram's already there. Our sketch the situations out, the values we need to find are written down. Things that we can keep in mind with this one is, like the ones before, we have a net force in the x and y direction. So we have an F net y. I'm going to say this is, again, 0 like the previous ones. Now our F net in the x direction, that is only going to be our force of friction. Since there is no applied force here, because the person is just coasting, delta Fx is the same as F of F. So we can find force of friction by utilizing mu, or we can find force of friction by utilizing Newton's second law, whichever one happens to work for this situation. Now, considering we don't know mu, we're going to use Newton's law way. So we have an initial velocity and a final velocity and a distance it takes something to stop. Going back to kinematic equations, we can find the acceleration. All right, so we have our acceleration is negative 0.51 meters per second squared. What that negative is telling us is that it is decelerating first off, but it's accelerating in that negative direction, so our net force is to the left, which makes sense because our only force in the x direction is the force of friction, which we're drawing as being to the left. So that means if this is our acceleration, let's go ahead and plug that into our Fx net equation, figure out what that value is. All right, so our net force in the x direction comes out to negative 12.75 newtons, and we are going to say that is the same as our force of friction, so our FF is also negative 12.75. Last thing we have yet to do is figure out what the coefficient of friction is, so we'll use that force of friction equation with our F of F and find mu. And there's our final answer for the coefficient of friction of 0.05. And that solves number 4. On to 5. Okay, so here we are with number 5. We have a 0.5 kilogram ball rolling to a stop. We know that the coefficient of friction between the ball and the floor is 0.18, and that is it. At that point, we need to figure out what the acceleration is. That's what we're being asked to find out. So why don't we go ahead and find the force of gravity for this, and since the ball is rolling on a surface, it's not leaving the surface. We know that the Fy is going to be 0, which means that Fn is going to equal Fg. So once we know Fg, we also know Fn. All right, so we have both of these values now. The only thing we have left to figure out is the force of friction, because we need that in order to find out our acceleration. Because in this instance, we don't have any other force values to worry about, and the net force is what we need, and the net force here is just going to be the force of friction. So we get an F of 0.88 newtons. Now from there, since we said this is going to be the same as our net force in the x direction, go ahead and use Newton's second law with this, so ma equals ff, find our acceleration. And there's our final answer. The deceleration of the ball, because it's going to be slowing down, is negative 1.76 meters per second squared. So there's 5, on to 6. All right, so here we have our number 6. A person pulling a suitcase along a tarmac with the force of 159 newtons at an angle of 37 degrees. So that means that the handle is at an angle of 37 degrees, and that's how they're pulling it by. So what we need to find out is the normal force, the force of friction, and the mu value. Something that's said in the problem is that the constant velocity is here, which tells us that our components fx and fy both have to be equivalent to 0. Now that's going to help us in a few ways. And before we can get into those values, first we need to get this 159 and break that into components. We need to have that in the x and y directions. So we're going to go ahead and use the cosine equation for the fax and the sine equation for the fay. All right, so those are our values for the components of the applied force. Going back to these net force equations, if we know that the F net x is 0, that means our x components have to cancel each other out since there's only the two of them. So if our FAX is 137.7, our force of friction also has to be 137.7. Now our y component stuff, our F net y, has to equal 0, but our F net y is our force of normal up, our FAY directed upward, and our FG directed downward. So these three values, once combined, have to equal 0. So we get a normal force of 214.5. Now the reason why it is less than our force of gravity is because since you are pulling the suitcase up and to the right, you are relieving some of that force from what normal has to apply. Because if this all has to cancel each other out, the ground only pushes up with however much force it needs to. If you're pulling up on something, then that normal force can then decrease. If you happen to be pushing the thing into the surface, like downward, then that normal force would have to go up to compensate. So now that we have our Fn, we have our Ff, we can go ahead and find our force of, or not our force of friction, we can go ahead and find mu. And there is our coefficient of friction. And I believe that is all it asks for number 6. The normal force, the frictional force, and the coefficient of friction. So there we go. On to 7. Alright, so for number 7, we have the mother who's pushing her carriage with the baby in it. The combined mass is 14.5 kilograms, and it says she's applying a force of 110 newtons at an angle of 30 degrees. Now, if you think about like when you're pushing something like a shopping cart or a carriage or whatever like that, that when you're pushing, you're not only pushing forward, but you are also pushing downward. Otherwise, you'd be kind of lifting, like, attempting to lift the item. And that wouldn't be kind of like the normal way of pushing something. So we're going to put that angle as 30 degrees downward, and we need to find the weight, the normal force, the force of friction, and the acceleration. So since we have FA, we have the angle, we should first break that FA into its FAX and FAY components. So now we have our components to the applied force. We can go ahead and work some more at this. So it says that the cart is accelerating, so that means that our F net in the x direction is not equivalent to 0 here. Now the next thing is we do know that in the y direction, though, this thing is still going to be 0, because we're just pushing along the surface. So we're going to use this F net y equivalent to 0 to find a few things out. Now before we use it, we're going to go ahead and find Fg, because we need that for that F net y equation. So we have a 142.2 newtons as our Fg. So now that we have this, let's go ahead and bring this Fy down here and try and figure out what the normal force is going to be. Notice I have it as Fn minus Fay minus Fg because both the y component of Fa and Fg are downward, so they need to be subtracted from your normal force to then get that net force of 0. So now we have F normal, 197.2 newtons, which is greater than the force of gravity or the weight of the object because you are adding downward pressure onto this cart, so the ground has to push up more. So now that we have FGFN, we can go ahead and find our force of friction. Comes out to 27.6 newtons. Now the last bit here is to find the acceleration, and we're going to do that with our Fx net equation. And there we are. That is our acceleration of 4.7 meters per second squared. And our force of friction we already found. So there's everything for number 7. Next up is number 8.